Here we are continuing on with chapter 2. So we have just learned about the Bohr model of elements and their atoms. And so we learned about the electron cloud, and we're going to continue on with that conversation with the electron cloud. And so if we think of that Bohr model, that target model that we saw in the previous video, the outermost one, the largest shell, the largest ring in that target where electrons can be, is called the valence shell. And those electrons in it are the valence electrons. And so we're not going to get into too much depth in this course, but the valence electrons will always total up to a possibility of 8, except for if we're dealing with very, very small atoms of elements like hydrogen, helium, lithium, maybe beryllium. Otherwise, we're looking for 8. And so we have what's called the octet rule. Of course, octet means 8. And so atoms are usually happiest when this outermost shell, whichever shell number it is, the outermost one, is filled with 8 electrons. And so we can use this to identify which atoms might possibly bond together. And so I know in the previous video I said that some shells can hold 18 or more. If you really want to get into the order in which these fill back and forth, we don't always necessarily fill an entire shell before we jump out to the next larger. So if you just take my word, we're looking for the outermost shell to have 8 electrons, with the exception of those very first, hydrogen, helium, lithium, those very, very small ones where their first shell is shell number 1, it's full at 2. Okay, so it brings me to the noble gases. The noble gases are that very far right-hand column of your periodic table, which I'll pull back up here. We saw this in the previous video. Over here, we've got helium, neon, argon on the far right. Those all have a full octet rule in their outermost shell, a full 8 electrons in there. And so if an atom, however, does not have 8, it will typically bond with one of its neighbors to either gain electrons from it, to give electrons to it, or perhaps share electrons with it. And so this is an example of some atoms sharing electrons with each other. So here in red, we've got an oxygen atom. And so it's only showing that outermost shell, not all the others. We're only looking at the valence electrons here. And so this would be the nucleus, and then we'd have another shell, another ring in here, and here we've got the outermost one. That's the one we really care about when we talk about bonding. So oxygen has 6 valence electrons. It wants 8. So it's going to do the laziest thing. It can either get rid of its 6 or gain 2. Again, the laziest thing is to gain 2 or share 2. And so it will actually hook up in this case with a hydrogen, and then they're going to share both of those electrons, and we'll see that over here like this. And then it wants another electron, so it's going to share with another hydrogen on the left side here, and they're going to share both those electrons. It's going to look like this. And so you can see that these are actually being drawn close together, and now their electron clouds overlap. And so this creates a molecule. This has bound into a molecule. And so when we share electrons like this between atoms, this would be a covalent bond. In particular, this molecule that's formed is water, H2O. So 2 H's, 1 O, 2 hydrogens, 1 oxygen, H2O. Okay, so we want to be able to really quickly see how many valence electrons an atom of a certain element might have, and how many it would gain and lose to fulfill the octet rule. And thankfully, our periodic table is organized quite nicely. So here was oxygen, and if we count just these tall columns, not the short ones here, but just the tall ones, it's a number 1, 2, 3, 4, 5, 6. It's in the 6th column, 6 valence electrons. If we look at hydrogen, we saw the image of those hydrogens having one valence electron. In fact, it only has one electron at all. And so each of them had one valence electrons. They're in the first column. And so that would tell me that lithium, sodium, potassium, all of these, no matter what ring, what shell it is, their outermost one has one electron in it. Everything in this column number 2 here has 2 electrons. Now, again, we don't count these short ones. We're going to jump over everything here. Boron, aluminum, these would have 3. Carbon, 4. Nitrogen, 5. Oxygen, 6. Fluorine, 7. And then here's our noble gases that are happy with 8. And they're already fulfilled with their octet rule. So if you'd like to pause the video, you can do the same thing for sodium, chloride, fluoride, sulfur, potassium. How many valence electrons does the atom have, and how many does it need to gain, lose, or share to fulfill its octet rule? Okay, so if an atom happens to gain or lose an electron in order to fulfill its octet rule, it would be termed an ion. So an ion is a term that we use for an atom with a charge. Now, if an atom has to gain an electron in order to fulfill its octet rule, it's got its same number of positive protons, and now it's bringing on more negative electrons. So we're actually going to have a negative charge. If it has to lose an electron or give it away to some other atom in order to fulfill its electron, we can jump back down to 0. We can jump back to the previous shell. And so it's possible to lose electrons to a neighboring atom. And so we still have, again, the same number of protons, but now we're losing the negatively charged electrons. So my atom left over would have a net positive charge. Positive ions are called cations. Negative ions are called anions. And I like to think anions looks like onions are bad because they make you cry when you cut them. So bad, negative. Okay, again, atoms are most stable when they have their octet rule fulfilled, and so they'll bond with others to make that happen. So some atoms will bound together. When they bind together, we'll now call that a molecule. We saw the example of water. A molecule versus a compound. A molecule is more more encompassing than a compound. So a compound is a type of molecule that includes multiple elements in it. A molecule could have multiple elements, so it could be a compound, but it might also have 2 of the same elements. So O2, H2, those also count as molecules. So just a little bit of terminology as we're building these molecules with our atoms bonding. Okay, we're going to come back to this in a moment. Okay, so our 2 main types of bonding is ionic and covalent. And so ionic is stronger than covalent. Ionic involves ions, so when an atom actually loses or gains an electron, and they would actually come together with their positive and negative charges to form a salt, and we'll see that later. Covalent, on the other hand, is where our atoms share electrons. And so we saw this in the example of the water molecule a few slides ago. And when I think about ionic versus covalent, I think about tug of war. I think about the atoms that are involved in a bond on each end of a tug of war rope. And if one is really, really strong compared to the other in terms of its pull for electrons, it's going to be able to pull the electron right off its neighboring atom. And so some atoms, though, are so weak, they actually want to give it away. So that pairing goes really nicely when we have an atom that's really strong and wants to take on an electron, and an atom that wants to give it up. And so those are really easy to think of in terms of forming ions, and then an ionic bond between them. Covalent, on the other hand, is where each atom kind of wants to keep its electrons. And so we have this tug of war actually being played. They're actually tugging on electrons on this rope. One One atom might pull electrons towards it a little bit, another atom might pull, back. And so instead of being able to actually pluck electrons from one cloud and bring it into your own, we can't do that because the other atom's pulling back. And so here we have kind of this shared process where these electrons can have be able to really be present in electron cloud of two different atoms, and so they're being shared. We can have polar or non-polar covalent bonds. And what this means is if my two atoms that are sharing these electrons have the exact same pull for those electrons, then those electrons will be completely evenly distributed across the bond. So I think about tug of war where both teams are exactly equal. That flag in the middle of that rope isn't going to go to either side of that mud pit. It will stay in the middle. So those electrons aren't going to spend more time in either electron cloud. They're going to spend equal amounts of time in both electron clouds where they overlap. But if one is a little bit stronger than the other, so think about a tug of war team is a little bit stronger than the other, but not much stronger. You might see that flag on that tug of war rope go slightly to the right or slightly to the left of the mud pit, but it never actually, the other team doesn't ever actually fall into the mud because they're not that much stronger, that much weaker. And so that's what we call covalent bonding. So here again, we're still sharing electrons. Both teams are still hanging on, but one is a little bit stronger than the other. And in this case, the stronger atom will actually have those electrons that are being shared on its side of the bond a little bit more often. And so that would be called, again, a polar covalent bond. And these are really, really important. So if you're a little bit confused about this, which you very well could be if you haven't had chemistry, please ask questions, please review in your book. The ability to figure out polar versus non-polar covalent bonds is really going to come in even in this chapter. It's going to be important. Okay, so we've got an example here. We have sodium and chlorine. Sodium's got one electron in its outermost shell and chlorine has 7. And I'll tell you right now, chlorine has a very, very strong pull for electrons and sodium just wants to give it away. So chlorine wants to gain one and sodium wants to give one up to fulfill its octet rule, either add up to 8 or drop down to 0. So sodium wants to give it away. It doesn't even want to play tug of war. It automatically just gives its electron away. And so now we've got a chloride ion and a sodium ion. So the cation here with a positive charge and the anion here with a negative charge. And because they're positive and negative, they're just going to hang out with each other because opposites attract. And so this is our ionic bond. But here we've got two oxygen molecules, and if you're thinking about tug of war, two oxygen atoms. These are two oxygen atoms here on the left. And if you think about tug of war, neither one is really stronger than the other, so they both can pull these electrons equally. And so what we'll see then is they're actually going to share. And if you think about this, we'll have one pair of electrons shared between them here. And then, interestingly, covalent bonds can actually form double bonds, so we can have these ones share as well. And so we're showing that here. And now, both of these atoms originally have the exact same strength to pull electrons than the other atom. And so this would be non-polar. One oxygen atom is not much stronger, not any stronger than the other. So these electrons will be shared equally between the two. And then at the bottom here, we can see just the O and the O. So those are the symbols for oxygen. And then here we show with the two lines, each line represents a shared pair of electrons. So each line here shows a bond where two electrons are shared. Now the fact that there are two lines means that we have a pair of electrons shared here and one pair of electrons shared here. So actually a total of 4. Okay, so I want to show some examples here. I'm not really too concerned about the shape here, but I want to show that water, we had this example of water a little bit ago, and we saw that we had an oxygen and a hydrogen, and we look at each of these bonds separately. So I'll start over here on the right, this oxygen and this hydrogen. Now, oxygen is really strong in terms of its pull of electrons, and hydrogen is not so much. When we think about the periodic table, hydrogen is actually kind of in the wrong spot. So it's actually got a decent pull. It does want to take in electrons, so it'll share. And so we saw that a few minutes ago. And so when we look at this, okay, oxygen is pretty strong in pulling electrons towards it. Hydrogen's only a little bit strong, but it's not going to completely ionize. It's not going to completely lose electrons to oxygen. And so what we have here then is a polar covalent bond. Electrons, one electron from oxygen, one electron from this hydrogen, are both going to be shared across this bond, and we see that depicted in this line here. But they're actually going to be toward the oxygen a little bit more often than they will be towards the hydrogen. So I'm going to pull in this image here, and I want to just talk about one piece of this at a time. So just going to clean this up a little bit for you. Okay, so if we just think about one of these molecules at a time, this is also a depiction of water. So red is oxygen, and kind of yellow is a hydrogen. And we can see that these kind of triangles in between them kind of show that the electrons are closer to the oxygen side. And what that means is that oxygen has a partial negative, not a full negative, because it hasn't completely plucked an electron towards it, completely off of another atom, but it's drawn another one in its direction. And so we see that this bond is polar covalent, and the electrons are toward the oxygen side. So the oxygen is partially negative. Now, what I wish I had in this image here was this little squiggly D looking thing. That's the partial. So really this isn't a full negative. This should be a partial negative. And that leaves hydrogen as a partial positive. And so we've got that happening here with this hydrogen-oxygen bond, and we also have it happening over here. So we look at each bond individually. Okay, I'm going to come back to this image and show you just kind of what it looks like with methane. Methane has carbon and hydrogens around it. Carbon and hydrogen, each individual bond, neither atom is really much stronger than the other. So this would be non-polar. So we don't have any of those partial charges. And kind of the same with carbon and oxygen. We don't have a ton of polarity there, maybe a little bit. But we're really concerned here with water and methane up here, these two. Okay, so going back to water, because water has partial charges, partially negative oxygen and partially positive hydrogen, that means that they can interact with each other because opposites attract. So partially positive hydrogen from one water molecule and the partially negative oxygen from its neighboring water molecule will have what's called a hydrogen bond. And so that's when we've got partial charges, opposites attracting, and we happen to have hydrogen involved. And we're going to see hydrogen bonding a lot between different molecules and even different sections of the same molecule. So this is extremely important to understand. We've got a polar covalent bond within each molecule causing partial charges. And then those partial charges attract each other on separate molecules. And so that, if it involves a hydrogen, typically we'll call a hydrogen bond. And so this is much weaker than either a covalent or ionic bond that would form in an individual molecule. But it still plays a really big role in biology and what happens within our cells. Okay, so we're going to stick with water because water is extremely important to life. It's obviously polar. We just covered that. And oxygen, again, has the greater pull on electrons, creating within a water molecule. It creates a polar covalent bond. So the oxygen part will be partially negative and the hydrogens will each be partially positive, and those partial charges of neighboring water molecules will attract each other because opposites attract. And that's not just for water, that's for anything that has a polar covalent bond, and even ions because they are full charges. Now, importantly, anything else that happens to be polar is hydrophilic. So anything else that has many polar bonds in it, polar covalent bonds, or even ions with their full charges, they are hydrophilic. Hydro means water, philic meaning loving, so water loving. Non-polar things that are all completely non-polar covalent bonds are hydrophobic, water hating. And so this is an image of water and oil. Water is hydrophobic. Most of the bonds, I would say almost all of the bonds in oil are polar covalent. And so they really don't mix well with water. Okay, sticking more with water, water has different states. It can be a gas, so vapor, steam. It can be liquid, what we think of as water. And then solid we would call, of course, ice. And then what happens when you completely fill a water bottle with with water and then you freeze it? Of course, it expands and you might break that water bottle. And that's actually kind of important. So when we have these hydrogen bonds between different water molecules, we'll actually see that they create a lattice structure when they're frozen. And so actually spread those water molecules out further. And because they're frozen, they literally have less energy. Heat is energy. So they have less heat. They actually have less energy when they're frozen. So they actually get stuck this way with this lattice structure with hydrogen bonds kind of spreading them out. It slightly pulls these molecules away from each other. So you have the same amount of molecules in there, the same amount of mass, but they're taking up more space now. So it's actually less dense. And that's why we see ice floating. We care about that when we think about our drinks and things like that, ice floats, but also fish. If you think about our lakes in the wintertime when we get ice cover, if ice continuously sank to the bottom, you'd actually have a lake completely filling with ice. And then, of course, most life in there would die. So here is like an image of that structure, that lattice structure with hydrogen bonds kind of separating these water molecules out a little bit and actually pulling them apart from each other, making them take up more space, but they still have the same amount of weight, the same the amount of mass. So same amount of mass over more space makes it less dense and it'll float on top of liquid water. Water also has a pretty high heat capacity. So this means the amount of heat that's needed to either warm it up or cool it down by 1 degree Celsius. So for water, this is 1 calorie. It takes 1 calorie of energy to heat a gram of water. And this is 5 times higher than sand. So that's why, it takes water a long time to either heat up or cool down. So if you're on a hot summer day, you're walking through the beach and your feet get burned, but the water's still cool. But then at night, the sand is cold and the water feels warm, and that's because of the water's high heat capacity. We also think of water as a solvent because, like we said before, polar molecules, not non-polar, but polar molecules, can dissolve in water. And we can also have ions dissolving in water. And we'll have around these ions something called a sphere of hydration. So we saw before chlorine and sodium ions forming in an ionic bond. But when we dissolve that, and this is table salt, sodium chloride is table salt. When you dissolve it in water, we actually have what's called a sphere of hydration. So we'll have this in this case the chloride, the negatively charged ion, and then the water molecules, partially positive hydrogens, will kind of tract. And this will be, of course, 3D. Our screen shows it in 2D. But so you'll have this ball of water lined up nicely with all the hydrogens, partially positive, attracted to the partial negative chloride. And the exact opposite can be said for the positive sodium ion, the cation here. It's positive, its full positive charge attracts the partial negatives of the oxygens in the water around it. And so in a 3D structure, these will line up and form a sphere in the opposite way with hydrogen sticking out. Okay, so we're still talking about water. Water has cohesive and adhesive properties. So cohesion means that the water molecules will be attracted to each other, and this is because of those hydrogen bonds. And that's also why if you fill up a cup all the way and you add a few drops, a dome will form before it overflows. Or if you put just a droplet on the table, it will actually stay together as a rounded, sphere droplet before, if it gets, you'd have to have a lot of water in that droplet before it actually flattens. Adhesion is because of water molecules' attraction to each other, it can also be attracted to other things too that are charged. And so it can climb up, like capillary tubes, for example, which are really, really small plastic tubes. And I like to think of this in terms of how water kind of works up your pant leg. So if it's raining outside or if it's snowy outside and your pants are a little bit baggy or long, you'll actually have water wicking up through your pants, and that's how I kind of think of adhesion. And so here we see one impact of water having cohesion, those water molecules being drawn together with hydrogen bonds actually allows things to sit on top of that structure, sit on top of that water hydrogen bonding together. And so this is an example of a needle being put on the surface. This also gives us surface tension. And here's another picture of a capillary tube action, and so we call that capillary action, and this is what I was talking about with adhesion. Okay, so we're going to stick with water a little bit more, but we're also going to bring in pH scale. So if we have an acid or a base, an acid would give you hydrogen ions in solution, and a base would give something for that hydrogen ion to bond to. Water can either be an acid or a base, depending on what it's put with. If you put an acid in with water, water is forced to be the base. If you put a base in with water, water is forced to be the acid. So acids and bases are essentially opposite. One gives a hydrogen ion, one takes it. And if they're the same strength, they can balance each other out. We've got the pH scale of 0 to 14. And we have to, if we're talking about life and bringing this in with life, we have to be able to keep a somewhat neutral pH in most of our living organisms. Now, there are some examples, like for example, our stomach acid is much more acidic than the rest of our body. But for the most part, we try to stay near a neutral pH, which is right in the middle of this 0 to 14 scale. And so neutral pH is right about 7. And higher organisms do this by having buffers. So we have buffers in our esophagus, buffers in many other organs. And so we have kind of a combination of very weak acids and very weak bases. So if you eat or for some reason have something else that's very acidic, those weak bases can come in and help neutralize them. If we eat something basic, our weak acids can come in and help neutralize them. And so that's how we can kind of buffer our body from what we eat. And then so I'll leave you to think about heartburn on your own and kind of what that would entail. I'm going to bring in an example here of a buffer system. And so here we've got carbonate. So we can actually create water and CO2. But in another condition, we've got a buffer system where we've got the ability for this molecule here to act as either an acid or a base. And so in this case here, it's got 2 hydrogens to give off in the case of a base coming into the system. And we can see here an example of where it's given off 1 hydrogen, and this leftover is acting as a base. So if an acid comes into this system, if I eat something acidic, or if I have some sort of acidosis in my blood, then I can actually take that on, that H plus on from, you know, an acid that's been introduced, and this will act as a base. And then in the end, we'll have water and carbon dioxide, which is of course what we exhale. So this is a really important buffer system when we talk about, or when we think about the lungs and how we inhale oxygen and exhale carbon dioxide. If you have a buildup of carbon dioxide in your blood, you'll actually push this over into acidosis, which means you've got too much acid.